less than or equal to n, and this Qn we will now prove by induction. We prove by induction that Qn is true for all natural numbers n. So naturally here also we will have basis, induction hypothesis and all the usual things. So first of all we have to show that Q0 is true. Now what is Q0? Q0 is the statement that P0 is true. If P0 is true, then Pm is true for m less than or equal to 0. The statement if P0 is true, then Pm is true for all natural numbers m less than or equal to 0. This statement is obviously true. Why? It's because if you look at the variation of m, what does this inequality tell you? M is a natural number and at the same time m is less than or equal to 0. There is only one such natural number, that is m equal to 0. So the truth of Pm is already taken here to be the case. P0 is true, then Pm is true for all natural numbers m less than or equal to 0. Because 0 is the only such natural number, so P of m is true. So that's why this is obviously true. In this case, the truth is not vacuous, but fits trivially. So by Q of 0 is true, that is Q of 0 is true. Now we assume the induction hypothesis. Assume Qn is true for some natural number n. Okay, so this means what does this mean? It means if Pn is true, then Pm is true for all natural numbers m less than or equal to n. We now have to prove that Qn plus plus is true. So that would mean that whenever whenever Pn plus plus is true, then Pm is true for all m less than or equal to n plus plus. Okay. Now let Pn plus plus be true. Okay, let Pn plus plus be true. We now have to prove that P of all the lower numbers are also true. That is P of all the smaller numbers. Okay. But what is given in the statement of the problem, it is additionally given that for some particular natural number n, Pn is true. This is given to us. Okay. And using the truth of this and this induction hypothesis, what do we get? Since Pn is true, Pm will be true for all natural numbers m less than or equal to n. So, since Pn is given to be true, the induction hypothesis means this one, implies Pm is true for all natural numbers. Okay, I am not going to write natural numbers. I have written many times. So since the natural numbers are the only things we are dealing with right now, so it's understood for all m less than or equal to n. Okay, so now for which m do we have the truth of P? For all m less than or equal to n, and additionally for n plus plus also we have the truth, and that is what we have assumed. So now Pm is true for all m less than or equal to n plus plus. I can write this. It's because I have the truth of P for all m less than or equal to n and also for n plus plus. And since in the proof of the strong principle of induction I have already showed that there is no natural number between n and n plus plus, so I have covered all the natural numbers till n plus plus. Okay, so this implies Qn plus plus is true. So by induction, Qn is true for all natural numbers n. And what was our Qn? Qn was the statement that if Pn, you see this is the Qn, if Pn is true, then Pm is true for all m less than or equal to n. And that's what we had to show, right? So this completes the solution, and this is the backwards induction principle. So once we can show how to use this, suppose you have a statement whose proof is known to us at some stage, say for n equal to 100 we have the truth of this statement, P100 is true, and we are somehow able to prove that in general when Pn plus plus is true, then Pn is also true. Then this exercise tells me that P100, P99, all the way up to P0, all these statements are true. So that's how I have the induction run in the opposite direction. So this is where the section 2.2 ends. Okay.